All right, then we're going to do some example problems where we see how standing waves might be applied to IB test problems or in our activity or maybe future practical or lab work that we do. So we'll do a string problem and an air column problem. Again, just please take note, there are no formulas on the IB data sheet telling me how standing wave patterns are. You need to understand the idea, know where nodes and antinodes are, fractions of waves that they make up, and then everything else can be deduced from that. So here we have a string vibrating between two rigid supports, like maybe a guitar string or something. It's vibrating in its first harmonic, the most simple one in the pattern, which means that the string's oscillating back and forth between these two patterns. The middle is going up and down. We've got an antinode there, and we have nodes at either end. The diagram shows me at t equals 0. Draw the displacement of the string at time t equals 1/4 frequency. How much time is that? Well, it might be helpful. Remember that frequency and periods are inverses of each other. This is the same thing as 1/4 times the quantity 1 over the period, which that simplifies to t/4. So essentially what we've done is we allow 1/4 of a period to go by. So as this thing oscillates, as it goes all the way down and then returns back up, that's one complete cycle or one complete period as it goes down and up. So 1/4 of that period is just getting back to equilibrium. So 1/4, 2/4, 3/4, and then 4/4 take me back to the top. So after 1/4 of a period, the string is going to be in the flat position. Destructive interference is happening everywhere. So what it's done is it used to be here, it shifted down to the flat position. If I do the same thing for t equals 1/2f, 1/2f is the same thing as 1 over the period. That's the same thing as half the period. So we'll allow half the period to go by. So half the period means it's going to flip all the way to the lowest spot, and the other half of the journey is back up again. So the string's going to look something like this after half of a period. We'll have flipped from that up position to the down position. The final part of this problem says that the distance between the supports is 1 meter. And we're given the speed of a wave in that particular string. So notice we don't have to use the wave speed in a string equation, but we do have to calculate the frequency. And so maybe what sound is produced as the string vibrates, it's going to make sound waves at that frequency. So we have our first harmonic. In other words, the string's vibrating back and forth between these two positions. That length corresponds to 1 meter. And we recognize that it's either a crest or a trough, which is half of a wave. So 1 meter represents half of a wavelength. I don't have both a crest and a trough at the same time. So that's half of a wavelength, and the whole wavelength has to be 2 meters long. In other words, the rest of the waves over here, crest and a trough. Okay, we only get half of a wavelength fitting in there. And then once I know how long the waves are, I can use my wave speed equation to figure out the frequency of the vibration. So 240 meters per second equals f times 2 meters. 240 divided by 2 gives me a frequency of 120 hertz. It's kind of a low-pitched sound, but that's the fundamental frequency, the main note that string will make if it's plucked or strummed. Flip over to the last page here. We'll do an air column example. This is a really good example because not only does it kind of test our ability to set up these problems of standing waves, but also it sets up a good lab scenario, like maybe how you would measure the speed of sound using standing waves. So take a look at the diagram. We have a tube, an open tube. It's open at both ends, but one of the ends is underwater. And we have the top of the tube sticking out. And then a tuning fork produces a frequency of 440 hertz. So that's the frequency of the sound of the waves that are going into the pipe. The tube is slowly raised out of the water until the loudness of the sound reaches a maximum for the first time due to the formation of a standing wave. Standing waves represent places of really big constructive interference. So the waves are going to get loud. The sound is going to get loud. Essentially, what's going to happen is sound waves are going into the tube. They're going to bounce off the surface of the water, and they're going to come out. So we'll have waves going down, one's coming up. And if we get a standing wave, it will become noticeably loud. What's interesting about the standing wave pattern here is here at the surface of the water, even though the tube's open at both ends, the water actually forms a boundary. So this is going to act like a closed pipe at the water and an open pipe at the top. So we're going to have an antinode if it's a standing wave at the top, and then a node at the place where the water meets as those waves come in. Okay. So how is a standing wave formed? Waves of sound enter. They go down the tube and reflect off the water and overlap and interfere with the incoming waves. So as these patterns of waves overlap with each other, we get our standing wave pattern. State the position where a node will always be produced. As we just mentioned, that's going to occur at the surface of the water. Always have a node there. It acts as a kind of a closed end to the pipe. The tube is raised a little further. Explain why the loudness of the sound is no longer at a maximum. Well, the sound waves are coming out of this tuning fork, and we have a fixed frequency and we have a fixed speed of sound. So these waves have a certain length to them. And as these waves come down, only if the length of the tube matches up with the right length of the waves will we get a standing wave. Okay. So, raising the tube changes the length of the air column, but we could say lambda doesn't change. Wavelength of the wave doesn't change because the speed equals the frequency times lambda. And the speed of sound hasn't changed because it's still just sound and air. And the frequency of the tuning fork hasn't changed. So lambda is a constant. Okay, so we get lambda hasn't changed, but the length of the air column it's the wrong length. Doesn't allow a standing wave to form. So you could think about, if you had a length of an air column, only one frequency, only one particular wavelength will create a standing wave, okay, or one series of wavelengths, and harmonics will produce standing waves. But if you have the wrong wavelengths that don't fit, they're not going to work. So if you change the length of your air column, you got to find the matching wave for that to work. And we're just keeping the wave the same. It's always the same tuning fork. So there's only certain sets of lengths that will work for this. That kind of segues into the last part of the question. We're told the tube is raised until the loudness of the sound reaches a maximum a second time. So let's think about why it would reach a maximum the second time. We know that the top of I'm going to make a drawing over here. The top of the tube has to have an antinode, and that wherever the surface of the water is has to correspond to a node. So if we draw what that pattern looks like, we could have something like this, okay, where this is the air inside the tube and that this is the surface of the water right here. And whatever this particular length is the first length where we'll get a standing wave. But if we continue to raise the tube out of the water so that relative to the tube, the water level goes down some more, there's going to be another spot right here where if the water level is here, which is basically a longer tube, where we'll also get a standing wave. Now, I haven't changed the wave. It's the same wave before, the same wavelength. But there's two different water levels that will produce standing waves. And there's an infinite number of these, actually, as the water level keeps getting lower and lower in the tube. Okay, so we could say that these are various water levels that form standing waves. And in this problem, this is the first place where the water level is. And then we hear, we've raised the tube out of the water so that this is the next water level where we hear the sound getting loud again. We get another standing wave. And if we kept going, there'd be another one and another one. So if we read the problem, it says between the two positions of maximum loudness, the tube has been raised by 36.8 centimeters. So that actually means that 36.8 centimeters is the distance, the additional distance the tube has been raised. So it's the distance between the two nodes. So we know how far apart nodes are from each other. And between a node, we have either a crest or a trough. So regardless of whether we're talking about open and closed pipes or strings, nodes are always half of a wavelength apart. So knowing that, let's be careful with our units. We could say 0.368 meters corresponds to half of a wavelength. And then we're going to use this to figure out the speed of sound in air. And so therefore a wavelength, if I multiply by 2, wavelength of this sound is 0.3736 meters. And we know that the frequency that produced the sound is 440 hertz. So we're almost there. Speed of a wave is frequency times wavelength. So I can multiply those both together and we can determine experimentally how fast sound is traveling. And we get something a little less than the accepted value. Maybe there's some experimental error here. Get about 324 meters per second. So I hope it's helpful for you to see some examples as you get into lab work or solving problems in this unit. This is the kind of stuff IB would expect you to do.